Hi everyone, today we will talk about how to design shear walls. Firstly, we will define the shear wall. Shear wall is a structural member in a reinforced concrete frame structure. It is used to resist the lateral forces such as wind force and earthquake force. Shear walls are in general used in high-rise buildings, as example towers, which are subjected to high value of lateral wind and seismic load. Now we're going to know what is the parameter that affect on seismic design, which is how number of shear walls I need to resist the earthquake waves and make my building safe from failure. 1. Type of soil. 2. Zones. 3. Height of building. 4. Weight of building. Now we want to know what is the steps to design the shear walls. 1. Find the weight of each floor. 2. Find the center of mass and center of rigidity. 3. Find the eccentricity in x direction and y direction and the total eccentricity in x direction and the total eccentricity in y direction. 4. Calculated the base shear. 5. Calculated the floor forces. 6. Calculated the torsional rigidity. 7. Selected the first shear wall that we want to design it. 8. Draw the moment and shear diagram for wall forces at selected wall. 9. Find the temporary area of selected design wall. 10. Design the boundary element of selected shear wall. 11. Design the steel of selected shear wall. Now we want to know how to design the shear walls. In this video I explain how to design the shear wall by full example. This example contain a building. This building with 7 floors have 3 shear walls in y directions, the y direction, and 4 walls in x direction. I have gamma of concrete equal 24, the dead weight equal 14, F prime C equal 30 megapascal. I have the 3 shear walls in y direction in blue colors and the 4 walls in x direction in green colors. I find the center, the distance between the center of wall and the y-axis and the center of wall and the x-axis. Firstly, we will going to step number 1 to find the weight of each floor. In any building, there is many elements. To find the weight of each element in this building, as example shear walls and slabs and columns. In our example, I have shear walls and slabs. So I will going to find the weight of shear walls, which equal 7, which is the number of shear wall, multiplied by 4, which is the height of shear wall, multiplied by the length of shear wall, which equal 4, multiplied by 0.3, which is the thickness of shear wall, multiplied by the gamma of concrete, then it's equal 806.4 kilo in Newton. Then we're going to find the weight of our slab. The weight of our slab equal the area of a slab. Then we in many cases or in many questions we exclude the opening area, as example stairwell and skylight. Then the net area we multiply by the dead load of the slab. So the weight of a slab in our example equal 12.5 multiplied by 16, and then we exclude the empty area which equal 1.5 multiplied by 4. Then the net area of our slab we multiply by 14, which is the dead load. Then the weight of a slab equal 2716 kilo in Newton. Then after we find the weight of shear wall and the weight of slab, we collect these weights to find the weight of our building. So the weight of our building equal the weight of shear wall plus the weight of slab multiply with number of story. So in the end, the weight of our building equal 24,661 kilo in Newton. Step 2 is to find the center of mass and center of rigidity. This step is very important because the earthquake forces is effect on center of mass, then it rotated around the center of rigidity. So we must be careful when we calculated the center of mass coordinate and the center of rigidity coordinate. To find the center of mass, we use a table. As you see, we in each cell include first the area, then width of this area, then we find the center, the distance between the center and of this area to the distance between the center of this area to y coordinate. Then we take the center of this area distance to x coordinate. Then we multiply the weight of this area multiply with the xi. Then we multiply the weight of this area by yi. We then collect the value wi multiply with xi and collect the value in the column wi multiply by y, and going to now we find xm, which is mean the x coordinate of center of mass, that equal to total weight in x direction over total weight in the floor, which equal 7.86. And then we're going to find ym, which mean the y coordinate of center of mass, which equal total weight in y direction over total weight in the floor, which equal 6.04 meter. Now we want to find the center of rigidity. First we calculated the stiffness of shear wall by equation Ke equal 3ei over the long term as you see, and we explain each sample in this equation as you see, and we in the end find the stiffness of the shear wall which equal 1103.3. Then after we calculated the stiffness of one wall, which are the same value of others wall, we want to find the rigidity coordinate. We divided the shear walls to two groups. First the x direction walls that equal W21, W22, W23, W24, and we find the stiffness of these shear walls and find yi, which is the distance between the center of the shear walls in x direction to x axis, and we in the end multiply stiffness by yi. We collect the stiffness of all walls, and we collect the value which collect the value in the column k multiplied by y. Now we switch to another group which is the shear walls in y direction. In the end we find the x coordinate of center of rigidity, which equal total k multiply with xi over total of stiffness equal 8 meter, and y coordinate of center of rigidity equal total k multiply by y I over total of stiffness equal 5.88. Now we're going to step 3 to find the centricity Ex, Ey, Ex total and Ey total. First, Ex mean the differ between the center of mass and center of rigidity in x direction, and Ey is the differ between the center of mass and center of rigidity in y direction. And Ex total equal Ex plus or minus 0.05 multiply with the length in x direction of the floor. This term is the minimum eccentricity, so we called it additional value to Ex. If the Ex is minus, so this term 0.05 multiply with Lx must be negative, because we want to additional value which is the minimum eccentricity. Ey total equal Ey plus or minus 0.05 multiply with the length in y direction of the floor. The same case, 0.05 multiplied with Ly is the minimum eccentricity, and it is additional value to Ey. So it must be the same sign of the Ey value. Now we calculated Ex equal negative 0.14 meter, Ey equal 0.16 meter, Ex total equal negative 0.94 meter, Ey total equal 0.79 meter. Step 4, calculated the base shear. Okay, first we select the area criteria that we need to find it to calculate the base shear. We have V max and V minimum. Each of them have a specific equation. If V is larger than V max, then we take V max as a control value. If V is less than V minimum, then we take V minimum as a control value. I is an important factor. If I have hospital or schools, this is essential building. I must save it from collapse through the earthquakes. So I make this factor be higher and take it equal 1.25. But in our example we have a building, usual building, so we take it equal 1. And we have R, which called resisting system factor. We have in this example shear wall system, we take it equal 4.5. Then we have T, which called time period of multi-degree of a freedom system. We calculate it by the red equation, and we explain each sample in this equation to find the time period of. In the Vmax and V minimum equation, we have Ca sample, which mean acceleration coefficient, and we have Cv sample, which mean velocity coefficient. These coefficients extracted from both tables depend on the type of soil and the zone factor. These tables placed in the codes, such as example, if we have this building located in Amman, Jordan, and we have type of soil, rock soil, and this area in zone 2A. So we're going to table 16I and select the zone 2A, and then we find the zone factor, which include 0.15. Then we going to the table 1 to find the value of CA and CV. We have the zone factor, and we have type of soil, which is rock soil, and we find that CA equal 0.15 and CV equal 0.15. From the previous slide, we important factor equal 1, R equal 4.5 for resisting system shear wall system, and CT equal 0.0488, HN equal the height of building, that equal 4 is the clearance distance for each floor, multiply with number of floor equal 28, CA which is the acceleration factor equal 0.15, and CV which is the velocity factor equal 0.15. We find then the time period equal 0.594 for multi-degree of freedom. Then we going the basic equation V max, that equal 2055 kilonewton, and then calculated V which equal 1384 kilonewton. Then we calculated finally the V minimum, which equal 407 kilonewton. We know that V is located between the V minimum and V max, so it's okay. So the V which is the base shear for building equal 1384 kilo Newton. To make the subject be more easier, the earthquake forces affected on the building as base shear. Then this base shear is distributed to the floors, which we have 7 floors, and each wall or each shear wall is take about a part of the floor forces. So in each wall we have Q1, Q2, Q3, Q4, Q5, Q6, Q7. Q1 is a part of F1, Q2 is a part of F2. So after we find the shear wall forces, we're going to design the selected shear wall. Now we want to calculate the floor forces. We have the equation Fx equal Fy equal this long term as you see, Ft equal 0 if Ta is less than 0, and Ft equal 0.07 multiply with Ta multiply with V if it larger than 0. Okay, in this example, Ft equal 0 because the Ta is less than 0.7 second from previous slide. Now we looking in the table, and we calculated the floor forces. As you see, in the first floor equal 50 kilonewton, then 99, then 148, then 189, 98, then 247, then 297, then 346. Now we're going to step 6 to calculate the torsional rigidity. Torsional rigidity is the minimum force required to deform object by twisting. So we divided the wall to two groups, walls in X direction and walls in Y direction. The torsional rigidity in X direction equal the stiffness multiplied by y square, and torsional rigidity in y direction, the same equation, but we replaced y by x. Now K is the stiffness of the wall and Y is the difference between the Y value of coordinate center of wall and the Y value of coordinate center of rigidity, and X is difference between the X value of coordinate center of wall and X value of coordinate center of rigidity. Now to calculate the torsional rigidity, first we take the walls in X direction and we find the stiffness of the wall that equal 1103.3. Now as you see in the table, we find the total of stiffness multiplied with y. Then we take the walls in y direction and take the total of value k multiply with y, and in the end the torsional rigidity equal the torsional rigidity of walls in x direction plus the torsional rigidity of walls in y direction. I want to stop to talk about the moment of inertia we have in the shear wall. Moment of inertia around the y-axis and moment of inertia around the x-axis. I want to talk which moment of inertia we choose it in this equation to find the stiffness. If we take a wall in x direction, so we have note that Iy or moment of inertia in y direction is larger than the Ix, which is the moment of inertia around the x axis. So the moment of inertia in y direction is larger than the moment of inertia around the x axis, because it's easier if we note that the moment of inertia around the y axis is mean we have to pull out the shear walls from fixed support, and this is very difficult and need a large moment. But if we doing a moment of inertia around the x-axis is a core bending for shear walls, and this is not need a large value of moment. So when we have x direction walls, we selected or we choose the moment of inertia in y direction because is more larger the moment from the moment of inertia in x direction. In the wall in y direction is the Ix, the moment of inertia around the x-axis is more larger than the moment of inertia in y-axis, and the same reason because it's easier to bend but is difficult to pull out the shear walls from his support. Step number 7, I want to select a wall to design it. I select W21 to design it. See, in second step, I want to find the wall forces on this wall. So I have two equations, QXI. I use it when I have a horizontal wall for design, and QYI for vertical walls for design. I have in my case a horizontal wall W21, so I will going to a first equation. QXI have a two terms. In cases I will add the second term, and in another cases I will subtract the second term. So when I can subtract and when I can add it. So if I have earthquake in positive x direction, which will affected in center of mass, so the center of mass make a rotation around the center of rigidity. So if you know, the earthquake will be in positive direction, and the rotation through the horizontal wall W21 will be in negative x direction. So the two direction is in opposite direction. So in this case will be subtract. Now after we put the values in equation, we find that QXI equal 0.232 FXI, which means that the wall forces is a part of a floor forces to then going to design this shear wall. Now we're going to step number 8, draw the moment diagram and shear diagram for our selected wall. We have a wall forces for our selected wall, shear wall. From the wall forces we can draw the shear wall diagram that we start from the top of wall, then added the wall forces until we reach the base of building, which equal 321 kilonewton. Then we're going to drawing the moment diagram, which equal the wall forces multiply by the distance. Step number 9. Find the temporary area of selected design wall. Firstly, what is the temporary area? Temporary area is the area that the shear wall carry it in addition on its self weight. So how we calculate the temporary area? Temporary area, we take the distance from the edge of selected shear wall to another edge of next shear wall in two directions, x and y direction. As shown in the picture, the D2, it's a distance from edge of the selected shear wall W21 to the edge of the shear wall to 3. Okay, we take the half of this distance and add to half of this distance the length of the selected shear wall, which equal B8. Then in y direction we take D1 with which is equal from the x-axis to the edge of the next shear wall in y direction. This distance equal 4. So 4. So we take the half of number 4. So the temporary area will equal 2 multiplied by 8, which equal 16. Now after we selected the temporary area, which is 16 meter square, we want to calculate the load from slabs. We have axial live load and dead live load and self weight. Then we calculated the dead moment, the moment due to dead load, which equal the dead load multiply with EX, the distance from the centroid y-axis of temporary area to centroid of y-axis of shear wall, because the y-axis is the resisted axis in our horizontal wall. Okay, then we find the moment due to live load, which equal B LS multiply with EX, which is the distance from centroid y-axis of temporary area to centroid y-axis of shear wall, because as we say before, we have moment of inertia around y-axis is more large than the moment of inertia around x-axis. Then we find the ultimate axial load by the combination equation, and we find the ultimate shear force and ultimate moment that in the end equal ultimate axial load equal 300 and 208. The ultimate shear force equal 321, and ultimate moment equal 10,390. Step number 10. Design the boundary element of selected shear wall. To design the boundary element, we must going to many steps. The first step A is to check if we needed a boundary element or not. We have equation FC. From this equation, we knowing if we need a boundary element or not. If FC is larger than 0.2 multiplied by F prime C, so we need a boundary element design. If FC is less than or equal 0.2 multiplied by F prime C, so we don't need to design a boundary element. Any sample in the equation, I explain it in the under the equation. Now we put the value in the equation, and we find FC equal 15.672 megapascal, and then we convert it by value 0.2 F prime C, and we find that FC is larger than 0.2 multiplied by F prime C, so we are going to design a boundary element. We take as firstly dimension of boundary element 1 meter multiplied by the thickness of the wall, which equal 0.3 meter. Now we're going to step B to calculate the reinforced ratio. Now we assumed first the length of boundary element equal 1 meter. We first find the force T equal 0.5 multiplied by FC multiplied with L over 2 multiplied with the thickness of the wall. Then we're going to find the area of steel from the next equation. Then we're going to find the steel ratio in the next equation, which must be between 0.01 as a minimum value and 0.03 as the maximum value. Now we put the value in this equation and find the rho of steel equal 0.039, and this value is high because it's nearest of 0.04 value, so we must enlarge the length of boundary element from 1 meter to 1.2 meter. Now to find the rho of steel after we change the dimension, we find after we change the dimension rho equal 0.032 is acceptable value because it is close to 0.03 value. So if we try 25 bar meter diameter of bar 25 millimeter, we find that we must use 24 phi 25 millimeter for each boundary element. Now we're going to step C, ties reinforcing and spacing. If the phi of bar is less than 32 millimeter, so we use phi 10. If our phi bar is larger than 32 millimeter, so we will use phi 12 millimeter as ties. To select the spacing of our ties, we have three equations. We will put the values in this equation, and then we select the minimum value to be the control value. In our case, we have phi 25 millimeter, so the ties will be use phi 10 millimeter, and the spacing after we put the values, we find that 75 millimeter for first equation, it will be the control value. So in the end, the ties reinforcing will be phi 10 millimeter at 75 millimeter center to center spacing, center to center as spacing. Now step D, check the axial load capacity of boundary element as we was doing in the columns. We have phi Bn must be larger than the ultimate axial load that we find it in previous slide. Any sample I explain it under the equation, and after we put the value, we find that phi Bn is larger than B ultimate, and that's okay. Now we're going to step number 11. We're going to design steel of our selected shear wall. First, step A, we must decide if our selected shear wall need to design or use a minimum reinforcing steel ratio. From the equation you see, we can decide if our selected shear wall need to design or not. We have V ultimate equal from previous slide equal 321 is larger than the specification of code, and so our specification tend us to design the wall. So we're going to step B to select if we need to use one or two curtains. In our specification code is tend us to use one curtain. Okay, we're going now to step C to find the vertical steel of shear wall. We going to steel it as depend of minimum steel ratio that depend the equation if we have one curtain or two curtain. If we have one curtain, we use the first equation. If we have two curtain, we just divided it by 2, so rho minimum equal 0.0025, and B we use 1 meter for design, and thickness of wall equal 0.3. Then we find the spacing of this bar by the equation you see. So in the end, we find the area of steel and selected the diameter of bar we need, and selected the minimum spacing, and in the end we used 12 millimeter at 150 millimeter from center over to center as spacing. Now step D, we will select the horizontal steel of shear wall. We have this equation from code, and this equation must be larger than rho minimum, which equal to 0.0025. Each sample in this equation I will explain it under the equation. So we put the value in this equation, and the unknown sample is just the row of horizontal steel. So after we find the row of horizontal steel, we find it is less than the row minimum. So we use row minimum to horizontal steel. So we use a 12 millimeter diameter, and then selected the spacing as the vertical steel, and in the end we use 12 millimeter at 150 millimeter center to center as spacing. And in the end we have reinforcing the boundary element as vertical steel 25 millimeter as diameter, and use ties phi 10 at 75 millimeter center to center as spacing, and reinforcing the shear wall steel vertical steel phi 12 millimeter diameter at 150 millimeter center to center as spacing, and horizontal steel phi 12 millimeter at 150 millimeter center to center spacing. And thank you for watching.